Whenever you're talking about mutual inductance, you assume a current on one of the current carrying conductors that are separate. And then you find the flux through the other circuit caused by it. So for this one, I need the actual flux penetrating that inner ring here. So what I did was from I, assume I, right? Then after I assume I get H for this big coil of radius A, H at the center here. And if you remember that if you had a ring, like so, if this is the XY plane and you have a ring of radius A with a current I on it, and you wanted the H field at any height Z on the Z axis here, it was equal to I, A squared over 2 times A squared plus Z squared to the 3/2 power in the AZ direction. Now some of you didn't remember that, but I gave you the H field equation for the H field at the center. Do y'all remember this class? Give me a show of hands. How many remember this at least? All right. That one, if you're not, if you haven't been thinking about it, sometimes it takes a little time. So I gave you what the H field was right at the center, because at the center we know Z is 0, correct class? If Z is 0, then I have IA squared over 2A cubed, or I over 2A. You all agree with me there? I want to make sure you see what I'm doing. Everybody okay with that? That's the H field at the center of the loop. So here, the H field at the center, I'll call it at 0, is equal to I over 2A. And it was in the phi direction, or it's perpendicular to the loop, so I'm not going to worry about anything else. Now, if you have that, if I wanted the actual H field, because there were multiple turns, I just multiply it by the number of turns on the outer side. Y'all remember me going through this? So I don't remember if it was N or M. I think I put M there, but it won't matter in the end. So now that's the H field caused by a whole lot of turns, not just one. Now I need the B field, right? What do I do to get the B field there?
Multiply by mu.
Just multiply by mu, right? So now I can find the B field is simply equal to mu naught M I over 2A. And it's perpendicular, so you can say it's in the AZ direction, but at this point, so it doesn't matter. And then the real kicker, the thing that's so important is B is much, much less than A. So therefore, when I go to get the magnetic flux penetrating this loop right here, which would be the second circuit, I can say that actual integral of B dot ds, that's the B field caused by the secondary circuit on the primary, if you will. I can just say it's really the B field here is not going to vary versus distance. Some people assumed it was a log. All right, they somehow got a 1 over rho in there. Do y'all hear me on this one? We're assuming this is a constant. Y'all with me on this, class? That's the key thing to this. So if it's a constant, this is really just the B field at the center times the area of that loop. Well, the area of that loop is pi B squared, isn't it, class? Now that's the flux from the outer one linking one turn to the inner one. And I might as well just write this down. This is going to be equal to mu 0 M, if M is the number of turns in the outer, I over 2A. And then it's times pi B squared, but I'm not done yet. That's the flux linking one turn, right? And on the inner one, I had either, I think it's N turns. I had a different number of turns. I had 5 on one, 20 on the other, right? So that means the total amount of flux linked would be equal to, in this case, it's going to be M or N times that. And that means that now I get this product, mu 0 times I over 2A. And then it's times pi B squared, and then it's really M times N, where M and N are the number of turns. Now that's the total amount of flux linked from the outer circuit to the inner circuit, based on this assumption right here that B is much, much less than A. So the B field, the magnitude here doesn't change much. That's the linchpin of this one. And then to get the inductance, we simply divide this by the current causing. And that means this goes away, And that would be the mutual inductance. That's how you get it. Now, the mistakes were made by somehow assuming this varied as 1 over rho, and then you would get a natural log, but it couldn't be the natural log of 0, so you had the natural log of A over B, and you were trying to do things to manipulate, to make it look like, well, it seems reasonable at good points. That's how I was viewing it. Just be sure you know how to do this problem, all right, from now on. Make absolutely certain if that B field is about constant in there, you just multiply the total flux is the B field times the area. All right, that's it. And I want to make sure we don't make this mistake on other exams like the 5. Okay. Any questions about that? I really tried to go over this before you got it the day before. I tried to make absolutely certain that you had this and you should. And there was a problem that I assigned that was like this. Okay, that's the quiz. Now, about the homework I assigned, any questions about that? Maybe you know. Nothing? If you didn't do it, I understand. Because now we're into time-varying fields, right? Now we've got time-varying electromagnetics. It's no longer electrostatics. So I want to do at least one of these, but let me just recap the 2 things that become critical. Now Maxwell's equations become curl of H no longer is just J, but it's J plus the partial of D with respect to T. And then you have curl of E is equal to minus dB dt. Those are 2 things. Those are Maxwell's equations. They define all of electromagnetic phenomena everywhere. The coupler between all these is, or the coupling equations is B is equal to mu H, J is equal to sigma E, and D is equal to epsilon E. And one other one I'll put down is divergence of D is equal to rho V. So these equations allow you to manipulate those equations down into any kind of form that you need to solve the problems. Now, one of the things about differential equations that I found in general is unless you see them applied, unless you see these laws applied to specific problems, you can't appreciate them. Just writing these things doesn't do much for you as far as an understanding. You've got to see them applied. So I gave you some homework, and
You got one?
you got one for me.
Yeah.
Fantastic.
5.4.
Which?
Yeah.
Okay.
How many columns?
He's got it right.
Do you remember Maxwell's equations in physics? How many do? I don't know. It depends on the physicist you have teaching the course. Some people are adamant to start from there and solve everything. And some are just, well, this is the equation as it's applied. Go ahead.
At time t equals 0 seconds, 60 micro coulombs is evenly distributed throughout a 2 centimeter diameter silicon sphere.
So A is 2 centimeters in that sphere of silicon.
Yeah, that's the diameter, so the radius will be
Oh,
1.
diameter, sorry.
Yes. And he's looking for find the initial charge density. And there are a couple other parts of the problem.
Charge density as time goes on. All right, so this is a charge decay problem. And I want you to be attentive to this. Anytime you see that word, how much charge is left, or anything like that, always think in terms of rho V. Now this is a charge, total charge, right? The charge density, if it was uniformly distributed at t equals 0, I'll call it rho V 0, would be Q over the volume that it's spread about, which is a sphere. You all agree with me? All right. So that means this would be 60 microcoulombs over the volume of a sphere is what? 4/3 pi, and then it would be 10 to the minus 2 cubed, correct? It's 4 pi, A, or radius cubed is volume. Do you all agree with that? Volume of a sphere. Make sure you know what the volume of a sphere is. And what the surface area of a sphere is. It's 4 pi r squared. Gotta make sure you know those. Now just leave that alone, alright? That's a constant, you all agree with that? Now we come over here and we take a look at this first Maxwell's equation. I don't know if anybody remembers what I said this is called. There are two equations. They're both named after famous men. I'll give you a tip. This is named after Faraday's law of induction, Michael Faraday, all right? The other guy begins with an A. Anybody? Ampere. Ampere's law, right? This is Ampere's differential form of Ampere's law. This is Michael Faraday's law of induction, second one. Just if you can remember that, it's actually maybe on Jeopardy someday. You'll make some money for that. But anyway, you know, I'm just going to say two things, right? Because we've got a class here that gone through a long weekend. It's been tough. It's a big game coming up tonight. You've got a lot on your mind. But the weather, the game, and probably your general weariness always makes the last 4 weeks of the semester in the spring one of the roughest, because the roughest 4 weeks. So I'm going to just tell you that you're facing that problem now, whether you know it or not, probably. Because the weather's getting nice, you're tired, you don't want to be inside. But hang with me, all right? So getting back to this, I'm going to start here and I'm going to take the divergence of the curl. So when you get a divergence of a curl of H, by definition it's zero. That's zero. That's divergence of J plus the partial with respect to T of the divergence of D. Now the reason I took the divergence operator inside that time derivative is because time and space are different, really, they are allowable. You can separate that like this because this is a linear system. T and X and Y and Z are independent of one another in terms of the derivatives. All right, just go with me on that. Do you remember what I do next here? I'm going to get something called a continuity equation. I did it on Friday. Do you remember my next step? I bet you some of you do. Go.
Del dot D is going to be rho v.
Right, divergence of D is the charge density, right? So I'm going to go ahead and put it, I'll put it over here. I have 0 is equal to divergence of J plus the partial with respect to T of rho v. That's the charge density as a function of space and time. What else did I do? Anybody? See that? All right, now I'm not done yet. So J is equal to sigma E, but what's E equal to? D over epsilon, right? Y'all see what I'm up to? So this is, so now I can say divergence of J right here is equal to the divergence of, and I'm going to put it in there, sigma over epsilon D plus d rho v dt. And if you make the assumption, it's generally speaking a safe assumption, that sigma and epsilon don't vary spatially. They're not a function of position over a homogeneous material. You can take that out front and you get sigma over epsilon divergence of d plus d rho v dt equals 0. And what do I do with div d again, class? Becomes the charge density, and this is important. So this is called the continuity equation. Equals 0. The solution for this, it's a first order differential equation, is just rho v 0 e to the minus t over tau, and here tau is epsilon over sigma. Now this has an interesting name. This is called the dielectric relaxation time. And it's akin to R times C for decay in an RC parallel circuit. If you think about it, if you have a charge in a capacitor, you put a resistor across it, it decays, the voltage will decay or charge exponentially, and the time constant is RC. You all with me on this, class? So that's exactly the same formula. Tau is epsilon over sigma. As sigma goes to 0, there is no decay, because then this goes to infinity, and frankly, no decay at all. Okay, now back to this thing. Gotcha. Back to this problem. This is gonna be a certain charge density, right? They give you the charge density at T equals 0, or the charge equal to that. What is the question now they ask for?
After the initial, they're looking at how long does it take for the charge density to drop to 10% of its initial value?
All right, so just take a look at this at face value. We've got the equation, well, we need one thing. They say this is silicon, and silicon has a given epsilon and a given sigma. Is this undoped silicon or doped?
Pure, so unknown.
All right, so if you look at this, now, there's slightly different values you're gonna get depending on where you look. But if you look in the back of his book, he'll have the conductivity of pure silicon. And he'll have epsilon of pure silicon. And I think epsilon of pure silicon is around 4, but I gotta be careful because I'm not absolutely certain. Dioxides are different than pure silicon. But in the very back of his book, he has a set of values. And actually, now I gotta find this for you. I think this is on page 625. Silicon. All right, here we go. For silicon pure, it's got an epsilon relative, I'm off, of 11.8. And it's got a conductivity of 4.4 times 10 to the minus 4th. It's on page 625. So 11.2 is epsilon relative, and this is what? 4.4 times 10 to the minus 4th. Is that right, class?
11.8.
11.8, sorry. All right, so now we need to find the relaxation time. We need to find tau, that's epsilon over sigma. So that's gonna be epsilon relative 11.8 times epsilon naught over sigma, which is 4.4 times 10 to the minus 4th. This is gonna be an interesting one. So it's 11.8 epsilon naught, or 11.8. You might as well do it times 8.854 times 10 to the minus 12 over 4.4 times 10 to the minus 4th. You can give me that time in a second. But we're gonna get, I mean, y'all know that this is gonna be a time constant right here. Right? That we're gonna need. Do y'all agree with me? All right, now, what the value of that is unimportant, really. Next, we're gonna say rho v of t at any time t is equal to rho v 0, the initial charge density, e to the minus t over tau, right? We start off at t equals 0, we have a rho v, a charge density of just rho v 0, right? Because e to the 0 is 1, right? And t is 0. We start out with rho v 0. If we wanted a graph of this, it would look like this. If this is rho v as a function of time, it's doing this. It's exponentially decaying. So it started out here at rho v 0, and you want to know how long it takes to get to 0.1 rho v 0, right here. Agree, class? So what are you going to do? Just look at it mathematically. You got this equation, right? You set this value to 0.1 rho v 0. Agreed, everyone? So that means this is 0.1 rho v 0 is equal to rho v 0 e to the minus t over tau. And now you can see it's 0.1 Then I take the log of both sides, so I get natural log of 0.1 is equal to minus t over tau, and multiply this by tau, and then throw a minus sign, and that will be the actual value of time that it takes to decay down to 10% its original value, this value right here. But I need this time to solve that, right? So can anybody tell me what that is? somewhere of the order of 10 to the minus 7. Anybody? Okay. It's 11.8 times 8.854 times 10 to the minus 12 over 4.4 times 10 to the minus 4.
2.37 times 10 to the minus 7.
2.37 times 10 to the minus 7 seconds, that's fine. So now take that value and take the natural log of 0.1 times that value and throw a minus sign in front. What do you get for time? Natural log of 0.1 is negative, so it's going to be a positive number. Anybody? Anybody at all?
5.47 times 10 to the negative 7 seconds.
Yeah.
Did I give you the answers to chapter 5?
I don't-
Is that the answer?
No.
It's not the answer.
No, we don't know,
Yeah, I don't think you gave us the answers.
All right, well, I bet you it's the answer.
That's fine.
I don't know if it's, huh? Is that what you got? That's how you do this problem. It's a decay problem. Remember, all decay problems will have an exponential decrease in the actual charge density from the time peak charge density occurs. All right, that's just the way it works. Another problem you got for me? There's one good one in here. Can somebody send me an email to post the solutions for chapter 5? Anybody?
I got it. Yeah, I got it. I'll send you an email.
Okay, good. So there's one other row, chapter 5. Oh, I was gonna do magnetic lifting. I'll do that on Wednesday when it covers these things. But I have to do magnetic lifting. I wanna do 5.3. Because this is a problem this is a type of problem that will trip people up. If you haven't seen it before. Want to erase an intake on the game tonight?
Kansas.
I don't know who's favored.
Probably Kansas. I'll probably root UNC. Underdog.
College basketball is not something I'm very good at predicting, so my teams are out short for a couple of rounds. All right. So for that problem, 5.3, go ahead and give it to me.
A current density is given by J is equal to rho times epsilon, or rho times e to the negative 0.1 t. In the arrow
Per
direction.
meter, or I'm sorry, amps per meter squared?
Yes, in the arrow direction.
All right.
It says find the charge density after 10 seconds. It has an initial value of 0.
Okay, now, for this problem, if you're just given that, and they want, what they're looking for is the charge density, right? As a function of time, really, assuming that rho v of 0 t equals 0 is 0. Are you with me on this, class? So how do we do it? Well, I erased some of the stuff, but y'all remember how I had divergence of J plus the rho v dt equals 0, right? Do you remember that? That came from the curl of H equation, taking the actual divergence of a curl is 0, you get divergence of J plus the rho v dt. That's the continuity equation, remember that. It's akin to Kirchhoff's current law. When you have all the current going into a junction is equal to all the current coming out plus the accumulation of charge if it's a time varying problem. So this is the same thing, only it's the differential. Divergence of J is like the rate that current comes in and out. The rho v dt is the accumulation of charge, the rate of accumulation of charge. So they give us J and they want rho v of t. You all see this right here? Now, before I just brute force this with divergence, I'm going to show you something. If I take divergence of j here, that's equal to minus d rho v dt. So I'll put a minus sign over here. You all see I just separated that, right? I put the differential on one side with respect to t, and I put divergence of j on the other. Now if I integrate that, dt from whatever time, it can be from 0 to time t, now I get rho v of t, and I'll even do this. Forget this portion of the integral, just add a constant that we'll figure out. So this will be an indefinite integral. We'll add a constant so we can actually find out the value at t equals 0. Do you all follow me on this, class? All right, now, I need the divergence of j. Here's j. If you look in the back of your book, what's divergence of j equal to? It's 1 over rho. Remember, we only have a rho here times what? d rho, right, of what? Rho times j rho, in this case, which would be rho times rho e to the minus t, or 0.1 t. And then there are other terms. They're of 0 here because there is no jz plus 1 over rho. And this is the phi term, j phi. These two are 0. There is no j rho. Jz, and there is no j phi. So this is the divergence. You can take a look in your back of the last page of your book. Do y'all see it, class? Make sure you see this. When you do this, one of the things you can see, this is going to be 1 over rho. Now I have rho squared here, so the derivative of rho squared would be 2 rho. And then it's just times e to the minus 0.1 t. So the rho's cancel, and I have 2 e to the minus 0.1 t is equal to divergence of j right here. And now, I come over here, and I can say that rho v of t, what I'm doing here is I'm taking this equation, rewriting. I'm going to put a constant by itself, a constant, plus the divergence of j with a minus, so it's plus a minus 2 e to the minus 0.1 t is rho v of t. Do y'all see that, class? How I did it? Y'all follow me? Now we have to find the constant, but the constant's easy to get because it says rho v at t equals 0 is 0. Do y'all follow me? He gives us this. If you look over here, when t is 0, e to the 0 is 1, so I have c minus 2. Follow me on this, guys? Y'all with me on this? Therefore, what is c?
2.
Just 2. That's right. And that's the equation for the charge. Now, it asks for the charge at what time?
10 seconds.
What do you see happening here? At 10 seconds, what will it be? Rho v for t equal 10 is equal to 2 minus 2 e to the minus what? 1. Correct, class? Isn't that right? So that's really what? 2 times 1 minus, really, e to the minus 1, and I don't know, it's a value, it's less than 2. But that's how you do it. What is the value of this thing, the charge density, as t goes to infinity? T goes to infinity, what happens? 2, right? This goes to 0, right? But this is 2. It goes to 2. Yeah.
So we found the divergence of j was 2 times e to the minus 0.1 t.
at this formula. Oh, you're saying, I didn't do the integration, is what you're saying. Good point. Actually, he's right. I'm being a little sloppy about that. If this is J, then what I need to do, you're absolutely right. Rho V of T actually is going to be equal to some constant plus, and then it's going to be minus, actually, you're absolutely right. Minus the integral of 2 e to the minus 0.1 t dt. And then that would be C minus, and this is going to be a minus is a plus 10, my bad on that, times 2 times e to the minus 0.1 t. I should have integrated that. You're absolutely right. And then I have to evaluate this. So this value of C is actually going to be minus 20. The mistake I made is this, I get casual. I forgot to do the time integration right there. Right? And that would be rho V of T. And by the way, that means C would be equal to minus 20. But I do need to do that time integral. That was on me. You're right. Y'all with me on that? But it's really executing. The whole idea behind this is starting there, solve for whatever you need from the differential. All right. So now we're going to go through Faraday's law. That's the next part. Now I want to tell you these problems I gave you over the weekend. Please do them and make sure you understand how to do them. I want to go through Michael Faraday's law of induction next. Fine. This is really transformer action. So when we take a look at Faraday's law of induction, it's the curl of E is equal to minus dB dt. That's the general formula. When you take a look at this by itself, it means almost nothing. But here's how it's applied. You're going to go ahead and take a region like such. And we're going to say this is going to be some sort of a loop, a wire, conducting loop. And we're going to have a little differential gap right here, small gap, very small. And we'll put a plus or minus V there, EMF. All right, so there's going to be some assumed voltage developed. Now, we assume we have a B field in here. There's some B field inside there. And the way, in what he does is, I want to try to make sure I say this the way I understand. He's going to show you this on page 289 through 293, but the real way you have to appreciate this is by understanding we're trying to simplify an application so it's understandable. They just have this say loop in the plane of the board. You can see it has an area A, total area of that loop. That's it. You're assuming the B field's perpendicular to that. Now this part's important. When I go ahead and I integrate the curl of E dot ds over the surface, this is the actual surface integral, that's equal to the closed integration of E dot dl around the loop, but this is in the counterclockwise direction, and I have to make a point of that. It's equal to minus ddt of the integral of B dot ds. It's through the surface, which is the magnetic flux. Now, try to appreciate what I'm saying, why I'm saying it. the integral of E dot dl around a closed loop. What it's really saying is if you had the curl of E everywhere in here and you integrate it over the surface, it's the same thing as integrating around the loop this way, from here all the way around the loop in a closed way. It has to be done counterclockwise. Well, the integral of E dot dl over anything is a voltage. So this is really a voltage, but we call it a voltage that's due to EMF, the electromotive force. Now, I show you the little gap there. If there wasn't a gap there, that voltage would be distributed around that loop, but it would be driving current in the direction of a positive voltage of the E field, the impressed E field. Try to appreciate that. So what I'm trying to do is show you that if there's a small gap there, there's a time varying B field there, you're going to get this voltage, right? But that voltage assumes it's in a counterclockwise direction. Well, actually, if you're doing this integral, that's what you get. But you'll notice this is minus ddt of the integral of B dot ds over the surface. And that really is minus ddt of the magnetic flux flowing through that surface. Now, the best way to see this is with an example, and that's where I'm going next. You all had transformer action in physics, do you remember that? Depends on who you had and how they taught it. Probably the single best way to see this is with this problem. If you have a long current, say it's on the z-axis and it's a current I, and I is a function of time. So I can say I is equal to, I'll just leave it as I of t now. And now I have a loop in the plane of the board. And here's my loop. It has some height h, it's got some width w, and it's at a distance, call it a away from the plane. Now you can all see if you look at this, that there's going to be a B field created by that current into the actual board here. And that B field would be equal to mu I of t times, or divided by 2 pi rho a phi. Can you all visualize that? B field is going to be mu I over 2 pi rho, and rho would be this distance measured from the axis, right? Now, if you look at this law right here, I'm saying if I break this at just a point, have a differential gap, I'm going to develop a differential voltage, VEMF, that's equal to minus ddt of the integral of B dot ds through that loop. Do you all follow me on this? So, here we go. We've got to find the integral of B dot ds first. That's over here. And then the differential actual surface here, the differential element of surface would be equal to, it would be d rho dz a phi. And the limits of integration, remember I just put the B field in there and I'm integrating, I'm just solving for the flux. So the limits of integration of rho would be from A to A plus W. And the height is just from 0 to h. So that means the magnetic flux, when all is said and done, you get mu 0 over 2 pi, then you get I of t, and then you get the height times the natural log, because 1 over rho, d rho, is going to be natural log of really A plus W over A. And that's the magnetic flux. I'm just trying to show you the simplest possible way to get this. Now when I take a time derivative of that, put a minus sign, I come over here, and you can see what I really get. I have minus, and now I'm gonna take all the constants, and I've got a comment here. This is mu 0 times h times the natural log of a plus w over a over 2 pi. And then it's times the time derivative of I of t. And that's equal to VEMF. Can y'all follow me on this? Now here's something to know. The term right here is the mutual inductance. So what we have is VEMF here is minus the mutual inductance between the two circuits, the infinite wire and that square loop, times the IDT. Can y'all follow me on that? You know what mutual is? We covered mutual, right? Go ahead, ask. You're squinting your eyes. Am I writing? Yep.
You're good, you're good.
This is just mutual. I put down times the IDT.
Okay.
But it's a minus sign right there. That's it. But the thing I'm trying to make you understand is that when you do this right here, you apply Michael Faraday's law of induction to this problem that I showed you to get the voltage. And the voltage, by the way, is measured with a plus on top, minus on the bottom. So this takes a little time to appreciate. What you're doing is an integral of E dot dl in the counterclockwise direction, looking from the plane you're defining the problem. And so from outside the board this way, it's counterclockwise. Whereas on the other side, then the problem would reverse itself and be clockwise. But if I look at this for a moment, you'll see that the voltage, there's a negative sign here. So it depends on, is this derivative going to have the negative or positive potential on how this polarity is going to be finalized right there. Everybody follow me on this? At least appreciate the fact, the real way this polarity is, the absolute value of that polarity, or I should say, which side is true positive. It depends on the derivative of that. Let me give you an example. Suppose I of t was cosine omega t. Well, what's the derivative of a cosine? Minus, right? Minus omega times sine of omega t would be minus. That would cause this to be positive, right? The net effect. And if it was a sine, it would be omega cosine, which is positive. So it depends on the actual, the way that I of t is defined. It has to do with the actual polarity of that induced voltage. But this is simple. It's very simple to appreciate at least an induced voltage. Now, I always ask this as the next question. That's one term, right? What happens to that induced voltage if I have two turns?
Multiply by half.
If there's shellac turns insulated on top of each other, right? Doubles, right? If we have M turns, goes up by a factor of M. Do y'all follow me on that? And that's sort of transformer action, the simplest possible way to understand it. I'll give you some more problems in this. I want to spend time on Wednesday really going over some of these problems because there's a bunch of subtleties that when you do the problems that you'll start to wonder about things, and I can answer the questions. And I may do magnetic, the lifting force all at the end of this, because then you'll have everything you need to know about. You'll understand how time varying magnetic fields induce voltages, and the lifting force is probably a little easier to understand.